Hi! We ended our last video just before discussing the observations made by Hubble. We are going to pick up on that and discuss what details it is going to add to our picture of universe at the moment. So he, or assume more precisely his team, used their big telescope to measure the redshift of extragalactic nebulae. And later on, other researchers continued on with these experiments, but they measured the redshift of other objects in the cosmos, such as the galaxies. So after gathering the data, he plotted the redshift z versus the distance that these objects were away from us, and found out that there is a linear relationship between the two. So as you should know from your more elementary courses, the Doppler shift formula for wavelengths is given by this formula here. It's for the case when the observer is stationary and the source is moving away from the observer. If you don't know the proof of this formula, or if you don't know where it comes from, I have a link in the description which you can look at for the proof. So what I want to do now, I want to show the physical equivalent of what Z is. So this can be, you can find this formula in your textbooks, or I don't know, you just follow the proof. So you end up with this formula here. So you just divide the lambda emitted, or the lambda that was emitted, the original wavelength, in the both sides, and then take the one from this side to that side. You end up with this. And then you can say that this one is equivalent to lambda emitted over lambda emitted. So you will end up with this formula, which is our definition of Z. And so by this, you can conclude that Z that we have defined is equivalent to V over C, which is the speed of the source, or the galaxy in our case, and C in this case is going to be the speed of light. Or if it was sound, it would have been speed of sound, but we are dealing with light, so it's the speed of light. The beta, it comes from the relativistic notation, which I prefer to use beta. That's why I wrote it down, but probably people don't use it beta in cosmology that much. But yeah, that's it. So as you saw in the non-relativistic case, Z is equivalent to V over C, or beta, and so you can say Z is directly proportional to V. So by earlier results, where Z was was linearly proportional to R, or distance, we can say that their speed is also linearly proportional to the distance as well. So what Hubble did, he just plotted his result on a piece of a graph, and he found a linear relationship, as I explained, between the two. So he just wrote its formula down, where and said that V is equal to some constant, or proportionality constant, times by the distance that object was away from us. He named his constant, proportionality constant, the Hubble constant, where I don't know, maybe the other people named it after him. I'm not actually sure about that one. So as you can see, there is subscript 0 in these on this proportionality constant. That comes from the fact that we are this Hubble constant is kinda variant in the as time moves on or goes back in time. So h represents its value at this moment or at the present time. So when he plotted his data, he calculated his proportionality constant to be 500 kilometers per second per megaparsec. It's in this weird unit because it makes this number more reasonably sized. But he had made a mistake with his standard candles when he was measuring the distance of distances to these objects. So he had his Hubble's constant calculated wrong, which sounds a bit ironic, but it happens. Now, the best current value for the Hubble constant is around 70 kilometers per second per megaparsec. This leads to an age of universe by assuming that there is a linear expansion from the start to present time to a 13.98 billion years old universe. But since there is uncertainty around this value, this value might change as we get more accurate results. At this moment in time, there is a dispute going on between the results from two different experiments trying to measure the Hubble constant from cosmic background radiation and type 1 supernovas. To understand more about this dispute, please watch the video I have linked in the description. In the next video, we will discuss more about the physical interpretation of Hubble law and what sort of universe can explain the observation where, from our point of view, the more distant objects in the universe are more redshifted. So until next time, take care of yourselves.